welcome back everyone. This is part 3 of the developer roadmap where I'm going over this website called Roadmap.sh, and I'm going to be going over these topics here, where last video I just went over the front end. Video before that I went over computer science. In this video I'm going to be jumping over to AI engineer. I'm going to be starting with the topics that are the easiest for me, and me being an AI engineer, the University of Hawaii, and working with a startup, this is a topic I feel the most comfortable in. Alright, so what we're going to be doing is following through each of these topics here, and we're going to be going over them one by one. This is my take on it, and hopefully everything you need to know to be a successful AI engineer. So the first thing that we need to know is, what is an AI engineer? An AI engineer designs, develops, and implements artificial intelligence systems. So what is an AI system? So an AI system is anything that does tasks for the human that requires human intelligence. So anything that has to do with problem solving, learning, or decision making. And this can include subtopics such as something known as machine learning, which you may be familiar with. The difference between the two is artificial intelligence is like if I were to create this as a hierarchy, artificial intelligence is at the top. And then the subcategories could be things like machine learning, it could be things in NLP, it could be things that incorporate rule-based systems, it could be just like basic algorithms that tell the computer what to do. These are all the different subcategories of artificial intelligence. What an AI engineer does is that it looks for each of these elements in these subcategories and merges them into a system that solves some sort of business requirement. So what is the roles and responsibilities for an AI engineer? An AI engineer does everything from designing the system, figuring out what data is available, cleaning the data. So this is a concept known as data wrangling. So data wrangling is when you do data acquisition, you scout for sources that you are trying to retrieve in order to solve a business problem, and data engineering or augmenting the data in order to basically pre-processing the data, removing any null values, and inspecting the data, visualizing it, and data modeling, which is basically training the model to do what you want based on your data. A huge part of being an AI engineer is having the data in the first place, because the data is telling you what your AI model needs to do. If you don't have any data, then you're just building a system that behaves based on your bias or your intuition, which may or may not be a good idea based on how much experience and what you think that people would do if you were to have data. Okay, so they work on data collection, cleaning, labeling, model training, testing, and so on. And they try to ensure high performance and accuracy. And so an AI engineer is also responsible of the performance of it, not in the respect of how accurate it is, but also how quickly it solves the problem. One of the things that I've studied a lot during my PhD journey is that when you're building a system to solve any sort of business problem using like machine learning or AI methods, you want to start with the least complex model as you can. And if that model doesn't satisfy the business requirement or have enough accuracy, then you want to upgrade the complexity of the model to gain that accuracy, but that also comes with a cost of inference time, which I'll get to later, is how quickly the model makes a prediction based on your input. Using a large language model might be very accurate for your use case, but if you use that right off the gate and you have a lot of large language model calls, it's going to take a lot of time for your system to come up with an answer. So using a large language model may not be something that you want, right? Okay, so what are their impact on product development? A product is basically any service that you're running. Something like Instagram is a product. And one example of how Instagram can integrate AI into their product, what they're doing now, which is the algorithm of giving content to you that it thinks that you will like the most. So at the most basic sense, say that you have a user, which is you are scrolling on Instagram and you see a few pictures you might like. So then you like a few photos, And then Instagram, on the back end, it'll capture those moments when you like a picture. So that's the data they'll use to train their model. They'll learn from what pictures that you like. So they'll take those pictures that you like, and as new pictures are coming into the system, they're going to basically do pattern matching on something as simple as the caption. Maybe they have some AI model describing what the picture looks like, and then it'll put it through this model that it trained for you, and then push it to your feed. And that's how it knows that the pictures that you're liking that's how it knows that it's going to share with you certain photos. Okay, so now that's where there's probably a lot of inefficiencies in that. So that's one way a recommendation system could work. But the way that they do recommendation systems now, I believe, they'll usually grab users who are using Instagram, group them in certain categories, and instead of building one AI model for each individual user, they'll build an AI model based on these categories of users. As a user, you probably fit in a certain bucket if you like a lot of cars. So they'll fit you in this bucket of people who like cars, and then other users who are also in your bucket, they will take the pictures that they like and give it to you on your feed. That's basically the TLDR of how recommendation system works for algorithm systems. So that's what an AI engineer does. It speeds up design cycles, optimizes processes, predictive maintenance. If there's a lot of users that are using a certain resource on Instagram or are accessing a database, maybe there's some allocation that goes on in the back end that makes the system more efficient in what it's doing, efficient resource management. Yeah. And then that's basically it. Just giving AI companies, they can innovate faster, reduce costs, and improve user experience. Okay, so AI engineer versus machine learning engineer. I think a lot of the times these two things are going to be used interchangeably. AI engineer, if you were to give it a strict definition in regards to a machine learning engineer, AI engineer knows how to put these models together into a system that works. Whereas a machine learning engineer knows how to build those models for the AI engineer. And that's basically it. Okay, so let's go into the common terminology. So AI versus AGI. So in a more basic sense, this whole paragraph is basically saying that artificial intelligence, as opposed to general intelligence, is that AI is something that's narrow. It's a product or a system designed to solve a specific niche. It doesn't solve all the problems out there. If you were to build a classifier that takes images of cats and dogs and labels the pictures cats, these are dogs, these are cats, these are cats, that's an AI system. As opposed to an artificial general intelligence system, so something like ChatGPT or Gemini, they can classify almost every animal that you put in there, not just cats and dogs. And that's basically what system is saying. Large language models are these huge language models. So they've been trained on billions of data, maybe terabytes of data, and they have billions of parameters to train them. So that might sound a little esoteric for now, but maybe I'll make a YouTube video on training a neural network. But basically, if I were to simplify this, then if you were to take a baby and you were to show a baby a list of animals, and then they have pictures on it, and then you point to each animal, and then you say, this is a cow, this is a dog, this is a cat. And then you'll ask them, what is this animal? It's probably going to get those answers wrong because they look similar. But as you go through them, this is a cow, this is a dog, this is a cat. If you keep going over it over and over again, it starts to change the parameters in its mind. So that's the parameters that these large language models are talking about. The parameters in the baby's brain, it's creating those creases in the brain to recognize patterns of what is a cow, what is a dog, and what is a cat. So a language model is basically, there's several different ways of creating large language models, but it's basically looking at a list of words like this, and then it's generating the most likely text here. Okay, I hope that makes sense for you guys. So I have a video on my channel called AI hallucinations, and I talk a little bit more about how large language models are trained. Okay, so next we have inference. So as I mentioned a little bit earlier, inference is basically how long it takes a model to make a prediction. You take a model that you've trained it. Now, how long does it take for that baby to identify or say what that animal is when you show it to them? That's what inference is. It gives an example of a self-driving car recognizing a stop sign on the road it has never encountered before. A self-driving car recognizing a stop sign on the road it has never encountered before demonstrates inference. As the car has cameras on it, it sees a stop sign. How long does it take for that car to recognize that this is a stop sign? You want that inference time to be as quick as you can in order to give the car the most leeway or the most headway. What's the word? I don't know what the word I'm looking for, but you want to give the car the most time to stop at the stop sign. Training is basically what I just talked about, updating its internal parameters to minimize errors. This is a concept of machine learning. You tell a model to make a prediction, and its prediction might be a percentage of how much it thinks it's a dog or a cat. Say you're building a classifier for detecting dogs or cats on images. You could train a model on if a picture of a dog is showing up, it's going to give you a percentage of how much it thinks it's a dog. The way that you can measure how wrong that model is that you subtract 68% from 1, or you just get 68% from 1, and then it's 34% it wrong or something. Then you can use that error of how wrong it was in order to update its parameters. And then there's another concept here later down in the list. It talks about gradient descent, which updates the parameters, and do you have to go negative or do you have to go positive? So embeddings. Embeddings are just numerical representations of words, sentences, or sometimes images, and you're putting it in a low dimensional space or a high dimensional space. So I have a few videos on this channel that goes into what embeddings are. So a computer only understands numbers. When you give the computer like a piece of text or any kind of image, it transfers those images and text into numbers. For a machine learning model, it also needs to understand numbers. It doesn't understand what text is. Even all of these words on here, just to give you guys like a basic example, all of these words, these individual unique words, they're converted into numbers. Embeddings are, so this is 1, 2, 3. And if I were to see another word here that says embedding, so since we map 1 to this word, we're also gonna map this word to 1. So 1, 2, 3, and then go through the numbers, and that's what the computer sees. So these words are mapped to numbers semantically, meaning that they have a semantic meaning for the number. If embeddings were mapped to the number 1, machine learning would probably be 1.5 or 2, or it would be very close to embedding. Whereas something like relationships, which may not do anything with embeddings or machine learning, it might be given a higher number like 56 or 57. Now we're gonna go into vector databases. So vector databases are, like I said, everything is represented as numerical representations. A database is basically just a place to hold all of that data. And then an embedding is, it could also be represented as a vector. And a vector is just the simplest way to describe what a vector is. It's an array of numbers. If you don't know what an array is, you can check out part 1 of this developer roadmap series where I talk about data structures. But yeah, that's what a vector is. It's just an array of numbers. And that numbers represents things like text, images, and audio. And the reason why you'd want to create a vector database is that it makes it easier for you to access that data. Some of the indexing techniques on grabbing information from this database have optimizations that make it easier to grab the data that you need. Because some of these vector databases can be millions of indexes long. So you need something quick and very accurate when you're retrieving those vectors at scale. AI agents, I think there's a lot of different definitions on what an agent could be considered. In this system, it's anything that is autonomous, that can perceive their environment, make decisions, and take actions to achieve very specific goals. I think NVIDIA has a slightly different definition of what an AI agent is. Their definition includes some sort of memory mechanism where the AI has access to the environment of what it's seen in the past, whereas this definition doesn't have it. So I think if you were to get a job as an AI engineer and you guys are in the world of building an AI agent, I think it's important to settle on a definition that you guys can agree to. There's so much different resources that say different things, but if you guys just have a shared understanding of what an AI agent is, it'll make you guys' life a lot easier. They can vary in complexity from simple rule-based bots to sophisticated AI-powered agents that leverage machine learning models. Nowadays, people are using large language models. They're connecting it to those models that have a lot of parameters and been trained on a lot of data. Whereas something like a rule-based system is like an AI agent, basically like a video game. I've taught a video game class in the past, and if you were to build artificial intelligence system in a video game, you would define states, and the state tell the AI what to do. So if there's a wandering state, the AI would go through a certain area. Maybe if you're building a spy game, it goes back and forth in a certain area. Once the person playing the game walks into their field of vision, the AI agent switches to a different state. Now it's detect mode or capture mode, where the AI agent is going to go after the user and try to catch them. Okay, RAG. I have a whole video about this, of what RAG is. You can go check it out. But the TLDR is mostly used in question and answering systems. So say you have a client and then they have this large document of text that they have these customers that ask them the same questions over and over, and they come to you and they say, I want to build a question and answering system for this document because I don't want to answer all the questions over and over. So what you can do is use something like RAG. RAG grabs the document they gave you and you can break up the document into chunks. You label those chunks based on what questions they answer. When a user asks a question, RAG will get those chunks from something like you'd store them in the vector database, and then it grabs those chunks, it sends it to a large language model with the question, and it comes back with an answer. That's what RAG is, which stands for Retrieval-Augmented Generation. And you can get that from the name. You're retrieving documents and augmenting the output of the large language model when it's generating an answer. They do this to make the model more accurate, so it doesn't hallucinate or generate wrong answers. It is used for tasks like question answering, summarization, and chatbots that require reliable, up-to-date information. Large language models, an important concept that you need to know is that they have a cutoff date where they only have information up to a certain date. And using something like RAG, it gives the model the ability to access new and relevant context to answer the user's question. Okay, so prompt engineering. I think there was a whole big thing of how prompt engineering was going to be a degree in some universities. So prompt engineering is a skill where you talk to a large language model by strategically designing prompts to optimize the model's performance. To give you a few examples of what prompt engineering can consist of, when you're doing something like image generation. So when you're very descriptive and use very specific adjectives to describe the image that you want, so things like using hyper-realistic, 4K, professional studio, so those kinds of adjectives help the model figure out what image to generate. For image generation, those matter a lot. Whereas if you were to build a system on automating a certain task, there's constraints that you want to put on the language model to generate a certain output. You would clearly lay out specifically what rules and constraints you want the large language model to output. So say you want model to output like a certain JSON that has a certain structure. Then you just include that information into the prompt and hopefully it'll constrain itself to whatever you describe. There's also a concept known as zero-shot prompting, one-shot and 2-shot. 0-shot prompting is just asking the large language model to answer the question. 1-shot prompting is giving the model a example of how you want that output to look like. So that's 1-shot. 2-shot is you just give 2 examples, and few-shot you give a few examples, and so on. All of these different techniques have to do with prompt engineering. There's probably a lot more prompt engineering techniques that you can use. There's chain of thought reasoning, tree of thought reasoning. Yeah, so if you want to do more research on how to improve prompts when you're talking to a large language model, you can do more research into that. But another important concept to learn is that the more text you put into the model and the more that you tell it to output something, and then of course it's going to take longer for the inference time on coming out with an answer for you. So just keep that in mind. Okay, moving on to pre-trained models. So a pre-trained model is basically models that have been trained in the past. This is, as we looked at earlier, a machine learning engineer is someone who builds models. An AI engineer is someone who puts those models to solve some sort of business problem. A AI engineer would leverage a lot of these pre-trained models that have been built in the past. Training some models, especially like the general like ChatGPT or the base GPT models or some of the BERT models or some of the like Claude, they're all like general models that can be adapted to solve a wide range of NLP problems, natural language processing problems, like question and answering, summarization, classification, all of that. The reason being is that when you're training these models, there's a lot of thought that goes into creating them. It's basically a function with parameters, and you're updating the parameters in certain ways to get a desired output. And then there's a lot of different like mathematical ways, or there's a lot of different ways you can manipulate those parameters on that function in order to get the output that you want. That's what this is saying here. A lot of general purpose models can be further fine-tuned to solve a different use case. When I say fine-tune, you have your GPT models, right? And those GPT models, they're trained to solve a wide range of problems. They can do question and answering. But if you have a very specific domain, like healthcare or something, it may not, because it can solve a wide range of problems, it struggles to solve very niche areas. In that case, you can further train the model or fine-tune it to be very specific in a certain domain, in a niche. So say you're doing something like physical therapy, and then you have another 50 gigabytes of documentation of physical therapy, what exercises to do, what diagnoses there are, what training formats to do or tests. You'd further fine-tune this model to adapt to certain questions or things in that area. Okay, so the benefits of using a pre-trained model, that you don't need to train the model from scratch. Training these models can take, sometimes it can take days, because there's billions of parameters in it, and then you have to ingest a lot of data to train the model. And then there's also cases where you might train the model in a certain direction and then need to do some changes to the parameters to make it learn better. That's what machine learning engineers, that's their bread and butter. They know how to train the model, but they may not necessarily know how to deploy it and keep it running or solve business problems. Quicker deployment, better performance with less data. You don't need to train the model yourself. Improve accuracy, generalization, and robustness across different tasks. Yeah, so you get the idea. The limitations and considerations when you're using these pre-trained models is that they may carry biases in their training data, and you don't know exactly what went into the model. So stuff like GPT, it said that they train it on terabytes of Wikipedia data and probably data that's freely available on the internet. But there's certain sources that you wouldn't want to train the model on because they have outdated information. For example, it may be wrong to train the model on research papers that have been between the years of 1985 and 1990. So say between the years of 85 and 90, there was some misconception of a certain health issue that was very popular. And if that data is used to train the model has some misconceptions of what it thinks of health. It carries those biases to answer future questions. And you don't have any control over that. All that data is baked into the model. You can further fine-tune the model by preparing extra data to tell the model, hey, stay away from this information. But sometimes there might be just too many examples in its training data where it has a tendency to produce wrong answers. It has this inherent bias in it. Okay, all right. Now we're gonna move on to OpenAI models. And this is basically, you have ChatGPT, GPT-5, and GPT-4, and they have a wide range of models in their disposal that people can use through their API endpoints. Whisper is their speech recognition model, and it's free to use. You pick a model based on your use case, and there's also models like GPT-5 is going to be better than GPT-4, and there's 4.0, 4.0 mini, O4. There's all these different models, and they handle text generation differently. Some are more accurate and some are less accurate. Some are faster and some are slower. You need to look at your use case, your problem of what you're trying to solve. You probably stick to 4.0 mini because it's a smart model and it's pretty cheap. I don't know the exact pricing on it. For all my projects, it's a fast model and I use it for solving some pretty complex problems. Then I'll try to do like prompt engineering. I'll try to do like these other things first of like representing my data using RAG or something like that. And then if that doesn't work, I can upgrade to a better model. Sometimes do all my development with a cheaper model and then use a more complex model for production because that's when I want very precise answers. Capabilities and the context length. Large language models have something called a context window. A context window is a limited size of how much the model can take at once in its context window. If you give too much data to the large language model, some of the text has to get cut off because it can't take all that text at once. So one way of getting around that, other coding systems do, because something like Windsurf and Cursor, they're able to handle these large repositories and they seem like they have this large context window, but they're basically representing the code and the information that it has in a different way. Sometimes it uses summarization. As you're talking to it, you might notice that there's a little indicator on there that shows how much context it's taking up. And when that context starts to overfill, then it'll take all the chat generate. It'll probably go through its own large language model to summarize all the content. So that way it has bits and pieces of the information throughout the conversation. Sometimes it's a good thing, sometimes it's a bad thing. The main issue with that is you don't know what is going into the context window. Okay, so cutoff dates. If you're using a base version of a GPT model, you're not using any Retrieval-Augmented Generation, then these models have a cutoff date, which is the point at which the model is not receiving any new information. They said the cutoff date for the GPT-4 is October 2023. So this is probably when the GPT model was finished training. So now in 2025, December 2nd, if I were to ask it a question of things that have happened recently, like what do you know about Gemini 3, it doesn't know that information because Gemini 3 just got released a few weeks ago. So it only knows information up to October 2023. The way that you get around that is that you use something like RAG, right? Where you're giving more information to the large language model to learn. Okay. This is probably where I'm gonna end part 1 of this part 3 series. I'm probably gonna break this up into multiple videos because I'm an AI engineer and have a lot of information and knowledge to share about this area. I'll see you guys in the next video. Thank you guys for watching. Please subscribe if you like this series. It really helps keep the channel going, and I'll see you guys next time.